Actually, we know what this is going to evaluate to. This is going to evaluate to pi squared over 6 in the end. So that's actually quite an easy formula to evaluate pi, because we can just multiply both sides by 6, it's not equal to 0, take the positive square root, and then we are done. Good morning, fellow mathematicians. Welcome back to another video. We're going to deal with this integral right here. I just recently saw 2 days ago under my video an integral with a surprising result. Someone suggested it to me, so we are going to give it a shot, and I would like to do this video a little differently. You are going to see it in a minute. At first I would like to deal with this thing right here, and that's actually the last method that came to my mind, and it's the most obvious one, but I just didn't look for it most carefully. So what we can do, we can substitute this denominator as being, for example, let's be absolutely dull. Let's say capital sigma is nothing but, oh holy boy, x squared minus 1. What we can do, we can differentiate both sides with respect to x to get that, well, 2x dx is nothing but a day sigma right here. We can divide both sides by 2 right here, because if we have our x dx, that's just this chunk right here. Meaning we're going to have x dx being nothing but d sigma over 2. Also, we want to solve for x, because we have this natural log of x right here, meaning we can just take the square root on both sides and add 1 at first. So we get sigma plus 1 is nothing but x squared, taking the square root. We're going to get this. I want you guys to notice that x is strictly positive on this interval, meaning we are bound to have a positive third right here. Now we can plug this chunk into here. We are going to get an integral running from. If we plug 0 into here, we are going to get negative 1. If we plug 1 into here, we are going to get 0 as the upper bound. Also, we have this 1/2 term. We are going to bring it to the outside. Then we have our d sigma. Also, we have x dx was nothing but our d sigma. We have something over sigma. That's what we have right here. And we have this natural log of the square root of sigma plus 1, but square root is nothing but to the 1/2 power. So we have sigma plus 1 to the 1/2 power. I'm putting it that way because, well, we can use the natural log property to bring this 1/2 to the outside, this power to the outside as a scalar. So we are going to get 1/4 right here. And this integral might seem quite familiar. That's actually the integral with the surprising result. That's nothing but pi squared over 6. Meaning overall we are going to land at pi squared over 24. So that wasn't any kind of witchcraft, it was actually quite easy to evaluate, but like I said, that was the last method that actually came to my mind. And I wanted to do this video a little bit differently, because maybe you guys are interested in what attempts I take to actually arrive at a certain result when dealing with integrals. So I have my notes here somewhere. Those are my notes. And we are going to take a look at methods I tried out at first. So what do we have? Yeah, at first, one thing that came to my mind, the first immediate thing, was integration by parts actually. Finding the antiderivative of natural log of x isn't too easy, you could say. That's why we are going to differentiate the natural log of x to arrive at 1 over x. And we are going to integrate x over x squared minus 1. Why is this easy to integrate? Well, if we take the integral of x over x squared minus 1 integrated with respect to x, we can just make a substitution. Let, for example, gamma, we are going to go overboard today with the Greek letters. Gamma be equal to the denominator once again, meaning we are going to derive at, well, d gamma being nothing but 2x dx. Once again, we can divide both sides by 2, cause why the hell not? And we are going to get that x dx, this very term up here is going to be d gamma over 2. So let's bring the 1/2 to the outside. Now we have just d gamma over gamma, and that's actually quite easy to evaluate. We are going to arrive at, well, 1/2 times the natural log of gamma, but gamma is nothing but x squared minus 1, so that's just natural log of x squared minus 1, so we can add a constant, really doesn't quite matter, we don't want this for our purposes, so we are going to have this right here. Now we can do simple integration by parts, meaning we are going to arrive at that our I is now nothing but, okay, this multiplied together, so we are going to have 1/2 times the natural log of x squared minus 1 minus this chunk together, yeah, minus 1/2 times the integral of natural log of x squared minus 1 over x integrated with respect to x. And don't forget, we have upper and lower bounds from 0 to 1, actually right here, and that's where I actually stopped, because, well, if we plug 1 into here, okay, that's yeah, a negative infinity times 0 situation, so we could use L'Hopital. If we plug 0 into here, that's where the problems start. If we plug 0 into here, that's going to diverge to negative infinity, and this, the natural log of -1, is something complex. So this turns out to be an absolute piece of shit, this part right here, so everything is going to diverge, and that's why I stopped here. So this stopped me in my tracks, and that's why this method didn't work out for me. That's why I started doing something different. Oh my boy, an uncut video, oh, behind the scenes. Moin, Timo. Just a second ago I said that this is going to be an uncut one, but no, Timo came in as always. So we are back. So this is more of an improvised video anyway, so I really don't care. Okay, next method. So we saw that this right here does kind of diverge, so it's bound to converge, kind of, because this integral overall converges, but I just didn't bother with it. So you can give it a shot if you want. Next up was my most favorite boy, Feynman integration, meaning we are going to say that we have an integral I of t, parameterizing it as nothing but x times the natural log of t times x over x squared minus 1. And this choice is absolutely obvious, because if we differentiate the natural log of t times x with respect to t, we're going to get rid of this x term right here. So if we differentiate that, then I prime of t is nothing but, well, 0 to 1, then we have this chunk times the partial derivative with respect to t on this term right here, so x over x squared minus 1. At first we're going to take the outer derivative, so that's 1 over t times x, and then the inner derivative is going to give us just x. Okay, so you see this and that is going to cancel out, and we are ending up with this right here, and we have actually found the antiderivative. It's going to give us 1 over t times 1/2, and then we have the natural log of x squared minus 1 from 0 to 1. And this is where I stop once again, because if we plug 1 into here, you are going to get something really fucking divergent, and if we plug 0 into here, it's going to be something complex. So that's absolutely disgusting. Yeah, that's why I stopped there at this very point with Daddy Feynman Leibniz rule. Last method I tried out before going absolutely insane was Taylor series expansion on the natural log of x. We have kind of derived this before, just the Maclaurin series expansion. You can make a change of variable. I'm not going to go through the whole process. The Taylor series I actually derived was, you can find it right here, I did a quick derivation of this stuff, just because is nothing but natural log of x. Someone else just came in. This video is absolute dog shit, it seems. So natural log of x Taylor series expansion is nothing but sum running from 1 to infinity of -1 to the k minus 1th power over k times x minus 1 to the kth power. And trust me on that, it's going to be absolutely horrid what is going to come out of here. Okay, so now we are going to get for the integral, that is nothing but the integral from 0 to 1 of our sum running from k equals to 1 to infinity, -1 to the k minus 1th power over k, x minus 1 to the kth power. And we also have this chunk left, x over x squared minus 1. We can actually factor that into x minus 1 times x plus 1 integrated with respect to x. So we can actually get rid of this thing right here. And Yeah, that's absolutely disgusting. So the next thing I did was drag stuff to the outside. That's not relevant right here, so just the sum. I'm going to put it like this. Then we are going to have this -1 to the k minus 1 power over k. And we also have this integral from 0 to 1 of, well, now we have x times x minus 1 to the k minus 1 power over x plus 1 dx. And I don't even want to know what my next step was. You probably want to know. Okay, let's get rid of this chunk right here. Okay, so you see we have x minus 1 to the k minus 1 power, and that absolutely screams for the binomial theorem, meaning x minus 1 to the k minus 1 power is going to evaluate to sum running from, let's say, j equals to 0 in this case. Was it 0 or 1? I'm always mixing this up. I'm terribly sorry. Yeah. From 0 to k minus 1, this exponent, k minus 1 over j, k minus 1 choose k, not over, and then we have x to the, it really doesn't quite matter how you do it, k minus 1 minus j, -1 to the j power. And you see, like I said, it's absolutely horrid. You can plug this chunk into here, and then you can actually drag the constants to the outside. You are actually going to get, so that's nothing but a sum running from k equals to 0, 1 to infinity of -1 to the k minus 1 power over k. Then we have the sum running from j equals to 0 to k minus 1. K minus 1, choose j. -1 to the j power. Integral from 0 to 1 of, okay. Now we have x to the k minus 1 minus j, but with this x we are going to get just, that's simplified so nicely, seriously. X to the k minus j power over x plus 1 integrated with respect to x. So yeah, easy peasy, lemon squeezy. Yeah, and one last thing to do, let t be equal to x plus 1. Okay, and then equivalently we can say that t minus 1 is nothing but x. So yeah, pretty easy on that one right here, and we can actually plug this stuff into here then. So I continue forward and actually got another binomial theorem out of here. That's basically how I continued. Yeah, absolutely disgusting. Let me do one more iteration. From k equals to 1 to infinity. -1 to the k minus 1 power over k. Sum running from j equals to 0 to k minus 1. K minus 1, choose j. -1 to the j power. If we introduce the substitution, we're going to get, okay, that's an integral running from 1 to 2 of, yeah, this is going to be a t minus 1, t series minus 1 to the k minus j power over t integrated with respect to t, because dt is the same as dx on this one right here. Once again, binomial theorem, k equals to 1 to infinity, -1 to the k minus 1 power over k, sum running from j equals to 0 to k minus 1, k minus 1 over j, 1 to the j power, integral from 1 to 2, then we are going to get 1 over t, sum running from I equals to 0 to k minus j of k minus j, choose I, and then we have t to the k minus j minus I, probably, or minus 1, yeah, k minus j minus I in this case, times -1 to the I power, integrated with respect to t. That's so horrid. You see this 1 over t, it's just this to the -1. Okay, we can bring stuff to the outside once again, so we are going to end up with k equals to 1 to infinity, -1 to the k minus 1 power over k. Sum running from j equals to 0 to k minus 1, k minus 1, reduce j, -1 to the j's power. Sum running from I equals to 0 to k minus j, k minus j I negative 1 to the ith power. Integrating this is quite easy. We are going to add 1 to this thing and divide by this chunk 1 over k minus j minus I t to the k minus j minus I from 1 to 2. And I wish you good luck to evaluate this thing right here. Actually, we know what this is going to evaluate to. This is going to evaluate to pi squared over 6 in the end. So that's actually quite the easy formula to evaluate pi, because we can just multiply both sides by 6, it's not equal to 0, take the positive square root, and then we are done. But I'm not going to bother doing this. You see, it's an absolutely monstrum right here, and this is immediately where I stopped, so this doesn't turn out any good. But if you did enjoy this kind of different video this time, it's just like Papa Flammy's improvised session, then feel free to subscribe, leave some comments down below, and I can do this more often. Well, you can support the channel by buying those t-shirts I created, and up until the next video, have a flammable day. See ya. Love you guys, appreciate ya.